Hi, my name is Corey Whittam, and I'm a master's student at the University of Maine in Orono. Today, I'll be talking about the age, structure, growth, and otolith microchemistry for white catfish in the Penobscot River in Maine. I'd like to start by thanking my co-advisors, Dr. Joseph Zaleski and Dr. Stephen Coughlin, as well as my co-author, Dr. Alicia Cruz Uribe from the School of Earth and Climate Sciences here on campus. To start off, I wanted to give a quick background on the range of white catfish in the United States. The species is originally thought to be native to the Atlantic coastal drainages from New York down to Florida, but since has been introduced all over the country and is found in coastal drainages on the West Coast and now further northward in the East Coast as well. So here we'll be focusing on this region in Maine, the Penobscot River watershed. And a huge contributor to the range expansion of the white catfish in this watershed is a result of the Penobscot River Restoration Project. So this was a project aimed at recovering diagenous or sea-run fish populations within the watershed. And so this resulted in the removal of 2 lowermost dams, as well as upgraded fish passage. But ultimately, it led to increased upstream access for white catfish as well. So a little bit of timeline for the species in the state. It was first found in a commercial bait tank in 1981. And then by 2007, it was first established or reported to be established in the lower Penobscot River below the lowermost dams. In 2012 to 2014, when the restoration project was occurring, those 2 dams were removed, allowing for upstream access. And by 2016, 2 years after the installation of the new fish lift, we started to encounter these species trying to pass further upriver. And so I've included a picture of a brown bullhead and a white catfish that were caught in the same survey, just to give you an idea of what these species or what white catfish look like in reference to our native catfish species, the brown bullhead. So attributes of white catfish, they're primarily found in coastal drainages. They have a high tolerance for salinity, up to 11 parts per thousand, and have been reported to exhibit seasonal movements up to 88 kilometers in river systems such as the Hudson River. And population declines have been recorded in their native range, as here we're actually describing population increases in their expanded or introduced range. So my research questions: what's the age structure of this population in the river? How have white catfish successfully passed further upriver of the lowermost dam? And do white catfish exhibit seasonal movements between freshwater and elevated salinities? So my sampling methods, first to collect all these fish, one was using the Milford Dam fish lift / trap. This is the newly integrated fish lift that was part of that restoration project that was first implemented in 2014. Fish enter that lift system when it's lowered, and they're raised, and they then swim into that runway that's currently drained in this photo. And before they pass upriver, managers have the opportunity to selectively trap or remove fish that they don't want to pass upriver at this point. An additional method was using baited trot lines in the lower river where electrofishing surveys or other sampling techniques weren't permissible. And we also, as mentioned, used boat electrofishing surveys in these riverine environments that were rather shallow but fast current, where we couldn't sample effectively with trot lines. So starting with the Milford Dam fish lift, just included a quick chart on the top right to show how an increasing water temperature, we show an increase in the fish that are present at the dam. So catch really peaked at around 22 degrees Celsius for when these fish start showing up. I've included a dashed red line as well as some asterisks over the 23 and 24 degrees Celsius mark, as those numbers aren't necessarily reflective of how many fish would be at the dam at that point. Just because of handling restrictions for Atlantic salmon purposes, the trap can't actively be fished during higher temperatures. But we do see a lot of ripe females coming up with eggs. And so we're suspecting these fish are likely trying to penetrate further upriver to potentially spawn upstream. And so here on the bottom is a plot of just the total catch for white catfish since the trap or the fish lift has been opened. We've seen an increasing trend in the total count, suggesting an increase in the relative abundance for this population within the river. But the 2020 and 2021 season have relatively low numbers, but this is largely because the trap was closed for 3 weeks or closed 3 weeks earlier than say the 2019 season, just because of warming water temperature. So those numbers in those years, recent years, aren't necessarily reflective of the increasing trend that we've been seeing. So to age these fish, traditionally you use a pectoral spine, and you can take a cross section at the articulating process. However, this often underestimates the age of older fish because the central lumen tends to erode away. So that's this portion right here. So instead, we use lapilli otoliths, and they were embedded in crystal bond resin and then sectioned with an isomet saw and imaged under the microscope. And for reference, these otoliths are about the size of a grain of rice. So not terribly large to work with, but we made do. So just some preliminary results of that work. Our total length for our fish sample ranged from 145 to 441 millimeters with a median length of 295. And our age ranged from 3 to 10 years with a median age of 5 years. And so we really lacked a lot of these younger individual fish in our sample. So to account for some of these younger fish, or as what we're hoping to get the projected growth estimates for those fish at younger ages, we use back calculated lengths at age. And so using the incremental distances between otoliths, we correlated that to the incremental lengths of the fish. And so we assume the proportional equivalence of the increase in the growth increment of the annuli is equivalent to the length of the fish. And so we produced a von Bertalanffy growth curve, which many of you are likely familiar with. And looking at the 3 parameters, K, L infinity, and T sub 0, we found very similar results from other studies that have looked at growth of this species. And so often newly introduced populations of fish species can exhibit fast growth because they may or may not have additional competitors or additional available resources. But here we see pretty consistent results with other well-established populations. So for a spatial distribution aspect, we had 3 sampling areas for just the trot line surveys. These are in the lower river beginning with D, and this is where the salt wedge or saltwater intrusion point is. So really we're not likely going to see fish downriver from this point. All the way up to A, where the Milford Dam is located. And so we really wanted to see, are there fish above the dam? And how many fish are we going to capture using this method? And so we had pretty consistent results with the 3 lower river sections, producing about 10 fish per 100 hooks on the trot lines. And we did catch 1 individual fish above the Milford Dam, demonstrating that these fish have successfully passed and that establishment is likely. They're just in very low numbers currently. So looking at the life history of this of white catfish, we used laser ablation inductively coupled plasma mass spectrometry. And this was assessed on a temporal scale, so beginning in the core region or crossing the core, moving outward. We did this because estuarine fish have been known to move between fresh and salt water seasonally. The estuary or brackish water tends to be a bit warmer during the winter months and can provide additional forage opportunities, whereas the fresh water can be a bit warmer and provide additional forage opportunities in the summer months. And so a basic plot of what these might look like of a fish that was spawned in fresh water but moved into brackish or salt water. You see elevated strontium moving from the core, which is that black bar that I've had in the center, or relatively to the center, and a decrease in barium, which would suggest moving out of fresh water. So barium is indicative of fresh water, strontium is indicative of salt water or elevated salinities. So some preliminary results from some of our samples. Looking at strontium, we don't really see any evidence for suggesting these fish are moving in and out of brackish water. According to much of the literature I had been reading, elevated levels of salinity would produce strontium calcium ratios greater than 2, and for a fish that say enters the full marine environment, far greater than that. And so we don't really see any seasonal banding patterns that would correlate with seasonal movements or really movements into the estuary at all. Now, looking at barium, as mentioned before, as a freshwater indicator, we did see a spike in barium right in the core region, but after that, the data was rather noisy and didn't suggest any seasonal movements, assuming these fish are staying in freshwater for the majority of their life. And so I've included a picture of a fry just at the top with its egg sac or yolk sac still attached to it, that it's using those nutrients, as this is likely a result of why we see this increased barium. Benthic spawning fish often have this increase in barium in the core, which is not necessarily reflective of the environment that it grew in, but rather nutrients from the mother fish that would have been incorporated into the yolk sac in a concentrated form for these young fish. And so rather than just producing line scans, we produce maps at a 5x5 micron resolution. And so I've included a picture of a 6-year-old white catfish here in the top, the transmitted light photo. Then we mapped calcite to show how the variation in calcite was relatively constant throughout the surface. And then we looked at the strontium calcium ratios as well. And we see a banding pattern that's consistent with the annular marks of the growth marks of these fish. And so this suggests to us that the strontium, the variation in the strontium signatures over the course of the life history of the fish is likely a result of the variability or the changes in temperature that the fish experiences. So as it goes into the winter months and those hard marks of the annuliths is formed, that's where we see those darker bands occurring where there's lower levels of strontium. And as it gets warmer, we see a greater deposition of strontium in those warmer periods. And we see a similar pattern for barium as well, not as obvious. But again, in that core region, you see that elevated barium. So it's not just revealed in those transects, but also revealed in these maps. And so part of my research is suggesting that if you have the opportunity to, producing some form of maps like these or additional line scans that are side by side to get a sort of bigger picture as opposed to small resolution to reduce some of the effects of that noise, because we don't really see these annular marks with the line scans as well as we do here with the maps. So conclusions, white catfish continue to expand their range higher into the watershed. Again, this is a result of dam removal and upgraded fish passage. Warming flow regimes within the river permit further passage of this species, and establishment upriver at this point is very likely. As permitting restrictions for species such as Atlantic salmon remain, but the water temperatures are likely continue to warm. If these restrictions are continue to be implemented, we'll see further and further fish passed upstream that are really untouched at the fish trap. For the otolith chemical or microchemical information, we didn't really see any any data that suggested seasonal movements between freshwater and elevated salinities. But again, this was for a subset of our sample. So in total, we had 491 fish. We ablated or used that laser ablation for 24 of those fish, and we ended up only mapping 4 of the fish. So it was a relatively small sample, but if we really wanted to get at this question a bit better, we would use acoustic tagging or radio telemetry to answer this question of movement, at least seasonally, within the Penobscot River. And so for future research, I'm curious to see how white catfish will influence our native population of brown bullhead, while flathead and channel catfish continue to outcompete white catfish in their native range. And so below, a picture of a brown bullhead and a white catfish captured in an electrofishing survey in the lower river, just to give you some reference for how similar these species really are within our watershed. And with that, I'd like to thank my funding source, the Penobscot River Restoration Trust, NOAA, USGS, the Nature Conservancy, and all those else listed there. A huge thank you to my field technicians, Bridge Osgood and Tom Cook, as well as the University of Maine Climate Change Institute for helping me with the microchemical portion of this work, and additional support from my lab mates within the Zydlewski lab as well. And I've left my email below if you have any follow-up questions you'd like to have for this talk. Thank you for taking the time to listen to this, and I hope you have a great conference.